Welcome to this video. My name is Mark Scythian. The date today is March 2nd, 2024. The title of this video lecture is Clausius-Clapeyron Equation. This particular equation can be used to compute water vapor pressure or liquid vapor pressure in general. So if you're working with combined cycle or steam applications, you cannot use the ideal gas law because water vapor is not an ideal gas. So most are reverting to the steam tables with respect to the evaporative state of water at higher temperature and the corresponding enthalpy and energy density involved. So using the steam table to deal with a non-ideal gas such as steam pressure and water vapor pressurization is the standard. However, using the Clausius-Clapeyron equation when dealing with water vapor pressure at moderate temperatures and pressures is highly accurate. The Clausius-Clapeyron equation provides a convenient method to calculate the vapor pressure of a liquid, especially liquids at moderate temperatures and pressures with respect to latent heat. So we are focusing on the product of liquid mass times its final temperature or its latent heat. So to describe the process of equation and iterations, we have a flow chart here. We have the liquid pressure increase as a function of temperature, described by the simple observation of pressure having an inverse relationship to the logarithmic relationship between enthalpy of vaporization delta H VAP divided into the R or universal gas law constant. So one component relevant from the ideal gas law equation times the general temperature. So this is a simple observation experimentally recognized. So we derive the given equation to support the Clausius-Clapeyron equation, for which the relationships then find a logarithmic ratio regarding the overall pressure ratio made equal to the enthalpy of vaporization divided into the universal gas law constant. This relationship is then multiplied times the inverse difference of the temperatures from final to initial. However, when used practically, the order of temperatures is an important aspect to rearrange. So while keeping the Clausius-Clapeyron equation, the CCE, constant in its original form, all that is required is to make the enthalpy of vaporization its ratio to the universal gas law constant in a negative product multiplier times the inverse ratio of the order of temperatures. So what all that means is, if we focused on a practical application, such as the vapor pressure of water as tested at an absolute temperature of 373 degrees Kelvin, its vapor pressure is equal to the surrounding atmospheric pressure, or has an atmosphere of 1.0 atmospheres at 373 degrees Kelvin. So if we were to subtract 273.15 from the Kelvin value, we would then compute the relative Celsius temperature value. So the vapor pressure of water is 1.0 atms at 373 degrees Kelvin, and the enthalpy of vaporization is 40.7 kilojoules per mole. So we're obeying a standard metric. Calculate the approximate vapor pressure at 343 degrees Kelvin. So we're inverting the T2, T1 with respect to order of temperatures. So now we actually can assume that the vapor pressure is substantially lower at 343 Kelvin compared to 373 degrees Kelvin. So when we apply the information to the CCE, we have the following equation plan here, and so the T1 is going to represent, in this case, the lower temperature. So we're taking the final temperature based off a metric that is observed experimentally and can be found in any type of vaporization or even steam table charts. The 373 degrees Kelvin, the water pressure vapor is at equal to the surrounding atmospheric pressure of 1.0. So assume we're in an environment that has 14.5 pounds per square inch atmospheric pressure at some given elevation. So that translates to 0.986 atms, because at 14.7 psi means sea level 0 MSL altitude, we have 14.7 pounds per square inch. So we then have a standard to reference the information that's calculated. So the T2 is the experimental reference point of the temperature of 1.0 atmospheres. So that's the simplicity of the CCE, is to take a standard that's recognized and then compute based on the order of temperatures. So that means the final pressure, the P2, is 1.0 atms, and the initial, or the 343 degrees Kelvin initial temperature state of the water is P1 or unknown. So all we have to do is apply the rules of mathematics to solve for P1. Substituting all the known information into the equation, we get the following equation form. The logarithmic relationship between the P1 and P2, with P2 known, made equal to the relationship of the enthalpy of vaporization for water at 373 degrees Kelvin is 40.7 kilojoules per mole. So we can write this in the complete joule value of 40,700 joules per mole, divided into the universal gas law constant, 8.3145 joules per mole degrees Kelvin. And then we set the order of temperatures up accordingly. So in this case, the T1 is recognized as taking difference from, and the inverse of them, their difference to the final temperature of T2, 1/373 Kelvin. So that reduces the equation down to the logarithmic ratio of P1 over 1 made equal to negative 1.1454. So to cancel the logarithmic function on one side, we find the exponential function on the other. So we take the exponential function of negative, taken to the negative 1.1454 power, and then this makes a clean standard ratio of the P1 to 1 atmospheres, and upon solving for P1 we compute 0.3181 atmospheres. The approximate vapor pressure at 343 degrees Kelvin is 0.3181 atmospheres. So the practical translation set up with respect to the US imperial system of measure is the 1.0 atms times the atmospheric pressure. So at 373 degrees Kelvin, the vapor pressure of the water is 14.5 psi, and the 373 degrees Kelvin is converted to Celsius. We subtract 273.15, and then we convert the Celsius value into Fahrenheit, so 99.85 times 9/5 plus 32, 211.73 degrees Fahrenheit. And then 0.3181 atmospheres times the atmospheric pressure. The 343 degrees Kelvin of water is exerting a vapor pressure of 4.61 pounds per square inch, and 343 converts to 157.73 degrees Fahrenheit. So our final answer here the vapor pressure of water at 211.73 degrees Fahrenheit is equal to atmospheric pressure, in this case 14.5 psi. The vapor pressure of water at 157.73 degrees Fahrenheit is approximately 0.3181 atmospheres, or in this case 4.61 pounds per square inch. So here we have the final answer written as the water vapor pressure differential, T1 to T2 and P1 to P2. So this can supersede steam tables, the CCE at moderate temperatures and pressures. And this equation, the CCE, is also relevant to the vapor pressure of any liquid at moderate temperatures and pressures. Thank you for watching this video, and have a great day.